But any measured quantity is always contains some uncertainty. So what do we mean by uncertainty? It means that we don't really know how accurate a value is. It could be exact, it could be close, it could be completely off. We never know 100% if something is certain. We can be accurate or precise, but not certain. The graduated cylinder here is the best example of this. It has what we call a meniscus, which, if you don't know, is the bottom of that curvature at the top of the liquid. So the liquid is going to curve down, and the bottom of that curve is what we call the meniscus, which is the thing we actually measure. The graduated cylinder is spaced out evenly by tenths, usually, depending on the cylinder, but in this case it's by the tenths. Having said that, we are never 100% sure how much volume we actually have, and the actual amount of volume is sort of guesswork based off of that tenth value. In this image, if you look at it, you can see that the 10th value is at the 26th milliliter line. But if you look at the image closely, you can see it could be slightly above the 26th or slightly below the 26th, meaning that it could be 26.1, 26.2, 25.9. In short, we are making an estimate of what the value is based off of what we're told, so we can never be certain of its absolute true value, which is why we round it to 26 mLs. Having said that, this is a good segue into the next topic of precision and accuracy. So having mentioned the graduated cylinder, we could speak about precision versus accuracy now. So the graduated cylinder in the previous slide was precise to the tenth place of an ml, because that is where the uncertainty is, and where we make our guess. Precision is not the same as accuracy. Precision is how closely many measurements agree with each other. So you take 5 measurements and they all get 25 milliliters. Those are saying they're precise to each other, whereas accuracy is how close they are to the actual value. If you know you have 30 mLs in an unopened bottle and you measure that out and you get 29 mLs, that's accurate to the 30, but it's not precise because precision is multiples together and accuracy is how close it is to the actual. So it's accurate to the 30 but not exact. Now, without that certainty, we have 4 possibilities of measurements here. A measurement that is both accurate and precise, both inaccurate and imprecise due to something called random errors or operator ineptness. We can have accurate but not precise if it's accurate but there's a random error involved. Or you can have something that's precise but not accurate due to systematic error. And what do those mean? So random errors, they occur by chance. They're unpredictable. They can impact both accuracy and precision. And those you're going to see things like voltage surges, change in temperature, gust of wind that are going to cause outside impacts that are going to change your value. You have air coming in that's going to blow the liquid in your graduated cylinder all over the place. Your meniscus is going to be out of whack now, so which means that you'll have to use it separately. Systematic errors, however, they are consistent errors. They come from measuring the instrument. They come from measuring instruments, so you'll see causes of measurements to be predictably off. So you'll have systematic errors are more like uncalibrated instruments and stuff like that. So take this example for now, precision versus accuracy. We have 4 students with a lead block standard known to have a true mass of 10 grams. So in this example, if we average out student A, right, we get 9.99, which is the average amount of the numbers. Now, in this case, it is accurate because we know the actual value is 10 grams. However, if we look at student B, we see that we have an average here of 9.79 grams, which is precise because if you look at all the numbers, they're all closely related to each other. 9.7, 9.8, 9.7, 9.8. That's consistency, which is what precision is about. But it is not accurate because it is not close to 10. It is 9.7 is the average. Student C, however, if you look at it, is both precise and accurate because you'll see multiple things. If you see 10, you see 10, you see 9.9, 10, 9.9. Now, if you average that out, you get 10.01. Even though it's a little higher than the 10, it's as accurate as it's going to get because it is 10. And the numbers are very close to each other. Now, student D, however, is neither precise nor accurate because the numbers don't add up to 10 in the slightest, nor are close in any way. If you look at 8, 12, 5, 1, average is 6. They're all over the place. If the actual value is 10 and you're getting an average of 6, something is wrong and your numbers are neither precise nor accurate. So, switching over to now sig figs, precision accuracy play a big impact to sig figs. In order to determine the degree of precision and the amount of certainty in the measurement, we must use each measured value with the appropriate number of significant figures. Now, they include every single digit that we are certain about, plus one uncertain digit. Like take the graduated cylinder, for example. You were certain that it's 26 in that line, but you don't know if it's 26.1, 26.2, 26.3, something like that. So, the key feature you need to know about why we use them is that the more digits you have, the more precise you are. So you will be asked in class during a chemistry course of your choosing, or whether you're in business or like you're in a company or something. If you're doing research, you will be asked to measure significant figures. You will be asked to determine the number to choose the correct answer, but your answer will determine on the number of significant figures. You'll see answers 25.1, 25.0, 250, 25, 25.10, 25.1. You'll see them, but they all have different sig fig rules because there's a list of rules you need to know, and only one of those will be correct. So, looking from the beginning here, let's start. The left column contains the rules here. So rule number 1, you see all non-zero digits are significant. So anytime you see a number that's not 0, it's significant. Rule number 2, zeros in the middle are also significant. So looking at 28.03, all non-zero digits are significant, so that's already 3 significant figures, and 0 is in the middle. So that is also significant. So that one has a total of 4 significant figures. Rule number 3, zeros at the beginning are not significant. So the significant figure would start at the first non-zero number. So in this case, 0.0038 would contain 2 significant figures because it would start at 3. And 0.0006 would contain 1 significant figure. Rule number 4, we said, this one is, you have to be careful because you pay attention to the decimal point. 15.0 has 3 significant figures. 15.000 is going to have 5 significant figures. Whereas 15 without a decimal point would only have 2. So that's important that you should know. Now, remember, the last thing I want to say is that zeros before a decimal point and after a non-zero number are significant. So 140, the 0 there is significant because there's a decimal point. So remember, decimal point equals significant, no decimal point equals non-significant. So now doing math with significant figures. Now this is an important thing because in addition and subtraction, the answer cannot have more digits after the decimal point than either of the original numbers. So let's look at this example to begin with. So we have 55.69 plus 23.5. So when you do the math normally, you get 29.19. Now you have to look at the significant figures of each individual addition option here. So 5.69 is going to have in total of 3 significant figures, but in addition and subtraction, you're only looking at the significant figures after the decimal point. So in this case, there's 2 significant figures after the decimal point. So that one has 2, and 23.5 has 1. So your final answer cannot have more than either of the original numbers. So it has to be, final answer must be rounded to 1 significant figure after the decimal point. So in this case, 29.19 is rounded to 29.2. So when it comes to multiplication and division with significant figures, the answer cannot have more significant figures than the least of the original numbers. For example, look at this problem. You have 6.856 times 2.11, which equals a total of 14.46616. Now, the difference between multiplication and division and addition and subtraction with significant figures is that with multiplication and division, you look at the total number of significant figures, whereas with addition and subtraction, you only look at the numbers after the decimal point. So in this case, you look at each individual thing. So 6.856 has a total of 4 significant figures. So, and 2.11 has 3 significant figures. So the final answer cannot have any more than 3 significant figures because it's the least number of sig figs in the original answer. So the final answer should have 3 significant figures. Now, it's important to know that you should never round until the final step because you can get some rounding errors at that point. So until this final step, you should write out 14.46616. Now your final answer should have 3 sig figs, so your final answer gets rounded to 14.5. Now this goes to show that you should also know proper rounding methods for chemistry. It also applies to addition and subtraction. 0 to 4, you round down. If it's 5 to 9, you round up to the next number. So, now multi-step calculations. We're going to do one advanced one to begin with. So we're going to keep all trails until the end because of rounding. So first thing you want to do, complete the math as normal, but keep record of all the steps. Remember, do not round. Then look at all the numbers to see a total number of significant figures. Step 2. So if we look at this generally, we're going to break it into steps. Step 1 takes care of that numerator, 23.651 minus 0.547, which gives you 23.104. Step 2, which is the denominator, is 879.1 plus 587.01, gives you 1466.11. Now, step 3 is going to be dividing all of that, which gives you that horrible decimal there, 0.001575871. So that's step 1, 2, and 3. Do them all. Go ahead, get your final answer, but keep a record. Now, step 4 is when we go back to things. So, determine the number of significant figures. So if we go to step 1, we look at both of those at the end has 3 significant figures after the decimal point and 5 significant figures total, which means that the answer for the top section can never have any more than you look at the total because your final step is division. So you're going to look at your total number of sig figs, which is 5 significant figures. Step 2, same thing. We have one significant figure after each decimal point. However, there's 5 total significant figures when you round that out. So it's important that you keep an eye out for that. In step 3, because step 1 and step 2 both have a total of 5 significant figures total in the number, the final answer has to have 5 significant figures. So that number that you got in step 3 gets rounded to 0.0016. Remember, take a look, be careful, know your significant figures. Remember, the final answer in addition and subtraction is based off of the number of sig figs to the right of the decimal point. However, if you're multiplying, you need to consider all the sig figs in that answer.